Alright, welcome back to the series where we're covering Unreal Engine's character movement component in depth. In this video, we're going to be doing mantling, so super excited for this video. It's taken me a long time to make, but it's going to be worth it, and I expect it's going to be very long. So what are we going to do? So we're going to do mantling. It's going to be a short mantle and a tall mantle for like different heights that you're trying to vault over. And as always, it's going to be completely networked, so this is going to work single player, multiplayer, any scale. I really made this one pretty reliable, so I'm pretty satisfied with this. And I'm also throwing a lot more polish into this mechanic. So in previous videos, I definitely was just trying to show you guys just the mechanic as it stands and keep any clutter out of it, but I really kind of went all out on this mechanic and added features that would really make it closer to a final game. So yeah, I think you guys are gonna really like it. So if you're watching this video and you haven't seen any of the other videos in the series, then I do want to disclose right at the beginning. So this has been a cumulative process. So I'm working on the code on the project that I made in previous videos. I have this project, the Zippy Unreal Engine project, that is kind of the showcase for all of the movement mechanics we've been creating. And it's the link is in the link for the GitHub is in the description, so you can just get the code right now, and you can see the code for this feature as well as all the previous mechanics we've made. But if you're coming here for the first time, I would say if you really know like a lot about the character movement component and maybe you've implemented your own stuff already and you have the fundamentals of networking down and are confident with Unreal Engine, then by all means you'll be able to understand this video completely. But if you're not really sure how the character movement component works, maybe you don't even know what that means, or you're just kind of trying to throw in mantling without like even using, say, like a character movement framework or anything like that, then this video probably won't be for you. If you do want to learn it, then I would say go back and watch like at least the first 3 videos of this series, because that will give you all the fundamentals to get to here. But if you don't really care about networking, then you're probably better off finding a like network unsafe mantle tutorial, because that'll just it'll be a lot faster for sure, and it'll be easier. So if you also, another big thing is we're going to be working completely in C++. So if you don't know C++, then unfortunately there's just no way to make networked movement reliable in Blueprints. Like, it's just you don't have access to the right functions, you don't have the right override capabilities. You just can't do as much. It's just not as powerful. This is kind of the biggest, I would say, barrier still in Unreal Engine. So yeah, for the few remaining, this is going to be difficult for sure. This is going to be the most difficult thing we've done, and it took me a while to make, but it's definitely worth it. So the features also that we're going to learn in this video specifically are going to be we're going to jump button override. So I want to make the mantle tied to the same input as the jump button. So like when you press space, you can mantle over something. And also, more specifically, I want it tied to the jump flag. And the reason for that is that we can reduce networking bandwidth because we're using the same networked variable. We're just treating it in a different way if we can mantle. Obviously, that makes sense, right? You wouldn't want to make a whole nother flag for mantling when it's kind of a sub case of jumping. So the next thing we're going to learn is we're going to do a ton of geometry testing, and I'm going to show a little bit of debugging process, how I go through that, because geometry testing can be a nightmare. We're going to do root motion again, and we're also going to learn root motion sources, which are different. You probably haven't heard of them, but they're kind of a useful way to transition the capsule. We'll see that later. And we're also going to look briefly again at my animation prototype workflow, just because we need to make root motion animations anyway. And so I just want to showcase, what buttons, what like checkboxes you have to click to get the root motion working. And, it's just part of the tutorial. So I'm going to obviously show you how to do it so that nobody gets lost in that. And at the end of it, we should have this, I'd say, pretty good looking jump, or pretty good looking mantle. The only thing, I guess, that is obviously in need of polish that is just out of the scope of this video is you can see that the hands often are like clipping into the wall or like going over the wall, and you'd fix that with like an IK thing. But it's just, it's not really movement logic at all. It's purely animation. So that would just take, I mean, that alone could easily take like another hour. So I don't think I'm gonna go that far, but you could solve the hand clipping and the knees clipping and all that stuff by just using like IK stuff, which you can, figure out in your own time. And then the last thing before we jump into the code is if you are working through this and you need help along the way, or something's not working, or you just want to ask questions, I created Discord for the channel, so that'll be in the description too. It'll also just be in my YouTube like about section, so yeah, you can join that. I think we have a pretty good start of a community, so people have already been asking questions. I've been helping them out. I think it's been going pretty well, so yeah, check that out. All right, let's get into the code. So the first thing we're going to do is actually in the Zippy character class, or in your character class. And that is, we are going to add a new variable here called pressed Zippy jump. So first we're going to override the jump input, and then we're actually going to do the mantle second. Because actually overriding the jump input has a little bit of nuance to it, and I really had to go digging through the source code for this one. So the reason why we're making this variable is, if you look through the source code, you'll notice that it's actually very similar to the default source code, which go here and find pressed jump. So they have this variable pressed jump, and basically it's weird. It's stored on the character, not the character movement component. But the character movement component edits it. So it's kind of a weird, I don't know why they chose to put it on the character, but we're going to try to mimic the behavior as close as possible, because I really don't want to, undercut source code. That's the most annoying thing when you're trying to like override some default mechanic in the engine, is that you don't want to manipulate the code in a bad way that might break other things. So I'm going to try to preserve the base class as much as possible, and just add our tidbit of implementation on top of it. But I do have to get a little nasty here, so we're going to make this jump variable, and then we're going to make these two overrides to jump and stop jumping. So let's go implement those. And the implementation of that is very simple. It's just going to be super call. Then we're going to toggle the pressed zippy jump to true, and then we're going to actually say pressed jump false. And then in stop jumping, we're just going to stop jumping, and we're also going to say pressed zippy jump to false. So what am I doing here? So let's go to the super jump to understand a little bit more. So in here, we say press jump is true and jump hold time 0. So like really simple. And in stop jumping, we just say press jump's false and reset jump state. So the reason why I'm overriding is really because obviously I want to get my variable to be true, but I also want to catch the press jump and set it back to false. So you notice here we set it to true, and then the value of press jump is utilized later, and it's important. But we are actually catching it and saying, actually, no, go back to false. Because the tricky part is we need to prevent the character from doing the default jump when we want to mantle. So we're basically stopping this. We're going to run our special mantle code before, and then we're going to set this back to true and let the jump run as it intended, but we just have to catch it beforehand. So this is all we need to do in the Zippy character, or in your character class. Now we can hop back into the character movement component for the rest of the video. Alright, so a lot of new variables to add. So I'm just going to add them all at the start. So we want to add a new flag. Call this saved pressed zippy jump. This is like sort of a flag. Obviously it is a flag, but it's not going to be compressed instead of the network. It's going to be consolidated into the normal pressed jump flag. But we're still going to keep it as a separate variable here because it is an important distinction. And then we have two other variables that are going to come in use a lot later, which is had anim root motion and transition finished. So we'll see why this stuff matters later. Then we're going to make an absolute megaton of parameters. So let's go that format. Yeah, so mantle max distance, mantle reach height, min mantle depth. Yeah, you can look through all these. They'll make more sense as we implement, but these are all sort of the control variables. So these are going to parameterize how you can mantle. For example, maybe you don't want to be able to mantle as far as 200 centimeters away, or you want to be able to reach a little bit higher, stuff like that. I'll explain them more when we're actually implementing it because it'll make more sense there. But these are just all the parameters we're going to use. And then here is a big dump of all the anim montages. So you can see there's a ton of anim montages we're going to use, and they each play their separate role in just creating a really high fidelity mantle. And this is also where I spent a lot more time polishing. Like, we could have just thrown in like one simple mantle montage, but it would have looked pretty crappy, and it certainly wouldn't have been reflective of what a real game would have. So yeah, we're going to go for a little extra polish here. Next we have, we need to put this, this is not a flag actually, this is just a regular variable, safe, had anim root motion. This was tying back to that flag we had that was saved had anim root motion. And then we also need to add all of these transitions variables. So we're going to explore what the transition is later, but yeah, you just need a bunch of transition variables to, basically this is going to handle transitioning into the mantle. We are also going to need some replication being done here. When I say replication in this context, I mean saved or replicated variables, which are for creating the fidelity on the proxy, the simulated proxy. So these variables are going to be for controlling playing the animations of someone else mantling on your screen. And it's mad at us because we need to make these functions. So we'll do that in a second. But first, we need to create a couple other functions here. So the first function is going to be update character state after movement. So yeah, just the complement to this function. Then we're going to come down and make another category for our implementation. So we're going to make the mantle section, and we're also going to make a helpers section that I'm starting. Probably should have made this a while ago, but I usually do this in big classes like this where I just have a couple helper functions that contain information that I need a lot. So yeah, deceptively small, just 2 functions, but this one's going to be massive. So, and then making these 2 functions for the replication on the proxy, just those onRep functions for that we required up here. So onRep short mantle and onRep tall mantle, and that satisfied the Unreal Engine header tool, so now that error went away. So that should be everything we need to do in the header. I just wanted to declare it all first so that we don't need to be jumping back and forth as much, and now we can get into C++ and implement it all. Okay, so first we're just going to make those saved move variables we created compatible with the saved move class. So we're going to, this is pretty standard. We've done this in all the other videos. We're just going to, implement the clear function. Then we're going to do get compressed flags. So this is where we are essentially clobbering this jump flag, right? So we are going to or equal the result of the jump flag with saved B pressed zippy jump. So now essentially 2 saved variables are both setting one compressed flag. And that's because both of these are going to operate under the same flags that we use less networking bandwidth, but the only reason that we trigger one over the other is the context. So, if we're not near a wall or anything, we will just jump normally, but it's only when we meet those conditions that we will actually mantle. And also the reason why I didn't call this like pressed mantle jump is because like who knows, I might actually use the jump button in another context where it's, you know, also very specific. Like maybe when you're swimming, you know, there's a special jump thing that needs to be performed, and I want to use the spacebar because I want to save another you know, I want to save a slot on our bandwidth, but I don't want to, you know, have to call my saved mantle jump. I just want to call the saved zippy jump. So that's for compressed flags. And then we need to do set move for. So pretty standard. One thing you will notice that is different about this is that we are getting the value of pressed zippy jump from the zippy character owner. So remember, this value is actually on the character, not the character movement component. And you'll see if I go to the parent class, that should be, yeah, here. You'll see when they get the jump value, where is it? Yeah, you get the character jump pressed instead of being on the character movement component. And I guess there's some other stuff too that is actually on the character. So I don't know why they do that, but that's the way they do it. So I'm going to try to stick with theirs as much as possible. And then the final thing for the save move variables is the prep move for, pretty much the opposite of set move for. You know, you should be fairly confident with what these are doing. This is just setting the values back into the character movement component if we need to replay a move. All right, so now we successfully clobbered the jump input button, but now we got to take advantage of that. So let's head over to update character state before movement, which is a function that we override from the base class, and we do a lot of stuff here. This is called just before. This is actually called before we start any movement. So this is before we combined root motion stuff. This is before we call the physics function. This is like pretty much the first thing called in perform physics, or sorry, perform movement. So we're gonna come in here, go to the bottom, start a new sequence for trying to mantle. So, oh, that's gonna be part of the debug stuff. I should comment that out for a second. So we are trying to mantle. We're only gonna try to mantle if that pressed zippy jump is true. So at this point in the code, the idea here is that if zippy jump is true, then we've just gotten that trigger from, like, say, the player pressing space, but we overrode the normal jump. So we're going to try to mantle, but if that fails, then we're going to, like, let the normal jump happen. So we're going to do this try mantle, and the reason that I do it like this is that I'm actually basically calling the can mantle and the perform mantle in the same function. I'm combining them. And the reason for that is that so much of the code that checks whether you can mantle is required for performing the mantle. There's just a lot of, you know, it's all geometry stuff. So we need to have that data in the perform mantle too. So I just combine it all into one. So this function, if it returns false, it means it, like, there was nowhere to mantle basically. If it returns true, that means that it already performed the mantle. So it'll only perform the mantle and return true if that was all valid. But if it wasn't valid, it'll not do anything and it will just return false. So if this is true, then we're going to call zippy character owner stop jumping. So that means that everything worked. We successfully prevented the jump, the normal jump. We're performing a mantle currently, and we want to, you know, turn all this off. If that was false, so maybe there's just no wall at all in front of us, then we want to say the zippy press jump is false, and then the press jump is true. So we're going to turn back on the press jump, turn off the zippy jump, and then we're going to call character owner check jump inputs. And this is going to be the line that performs the jump physics basically. So it's just going to do some stuff like, oh, did we jump? And obviously this would have been false. This is, you know, this function actually is called before this gets called. This function is called a while ago, but it won't do anything because we hard locked this value to false. So that's why we're basically suppressing it until after we've run our code, and then we're calling it manually, and that's going to do the stuff which, do jump, obviously the big one, stuff like that. So yeah, that's kind of the thing. It's not perfect. I don't like doing this. I don't like, manipulating the base class code because, you just never know like what potentially might break. And I've thoroughly tested it. I don't think anything is wrong with this approach. And it's pretty much the only way I can think of that will allow you to use the jump flag for another mechanic. But it is annoying that they don't make this a little bit more accessible in the source code. So yeah, this is my solution. And now we've pretty much replicated the jump mechanic. So now we are going to make the helpers. So we're going to come down under interface. I'm just going to paste all of them in here. They're pretty simple stuff. Basically is server just checks if the character owner has authority. That's a super simple way to check if the code is running on the server. Cap R stands for capsule radius. So this is just shorthand for getting character owner, get capsule component, get scale capsule radius, and same with capsule half height. That's cap HH capsule half height, same thing. So pretty simple, but I just use these, especially like these two values. I use these a ton, especially for the geometry testing stuff. So I figured I'd make them helper functions. And then the last thing before we start implementing the mantle is we're going to define these macros. So these are going to help us to debug easier. I define here a log function, which is going to print stuff to the screen, which is, these are all wrappers for Unreal Engine functions, but they make it a lot quicker and a lot, I think, easier to read. So this function just logs to the screen. This function just creates a point debug in space, line, capsule. And so what I have here, what I set up here is I have this if else macro. So if this is 1, which actually we should make it 1 for now, then all these macros are going to be defined. If it's 0, then they basically do nothing. So it's just an easy way for me to turn off the debugging whenever I want. Pretty much 0 cost. And also, do you need to include, so I do these draw debugs. I didn't actually include the draw debug helpers. You do need this, I'm pretty sure. Yeah, like you need this to be able to call these functions, I think. Although I'm surprised I wasn't getting any errors from that. Oh, because I haven't actually called these macros yet. Yeah. So now, finally, here, let's close this stuff up. We can finally start creating the implementation. So let's carve out a little chunk of space here. Okay, so I'm not going to paste the whole function in because the tri-mantle, the whole thing is going to be about like 200 lines long. So we're going to work through it step by step. That's going to be a lot easier for you guys to understand, I think, and also to catch errors that you might have, in the in-between parts, because there's just a lot of codes. There's a lot of, copying and stuff you might get wrong. So, okay. The first thing all we're doing is literally just logging that we tried to mantle. This slog for screen log. This is one of the macros we made. And then just returning false. So we're not actually doing anything right now. We're just testing to make sure this whole jump override worked. And hopefully, if everything worked, you're going to get the mantle was logged. And then since we're returning false, you should see the character jump afterward because it didn't mantle anything. But before we hop into the editor, we do need to implement some of the undefined functions here. So we'll just generate these definitions, but we're not going to actually create them just yet. So we just need to return the 0 vector here for these two on-reps. We'll just create definitions for those. Just give the compiler something to link to, and then I think we have just this last one, update character state after movement. So I'm just creating the definition for it. Make sure you call the super, obviously, but we're not going to put code into it just yet. So now let's hop into the editor and check this out. All right, so here we're in the editor, and basically you can see when I press space, it says failed mantle reverting to jump. That was actually one of the logs I created earlier. And then the log in the mantle, which was just tried mantle. So yeah, it seems like everything's working. And now we're going to actually make the code that will flip that to true when we get in here and actually try to do a mantle. All right, so let's real quick just go over all the stuff we're going to be doing, because basically this entire function will just be doing a ton of geometry testing to figure out if the capsule is in the right place and there's the possible ledges that it can go on. So we need to just do a ton of testing. So let's just demonstrate that here. Let's make a capsule. And we'll just make 2 different sized heights. So the first thing we're going to do is we're going to shoot out some lines out of the capsule to test if there's any walls in front of it. And you can see this one, we will get that hit. And that's going to show that there was a wall there. The reason why I'm shooting out multiple is because, we might have something like an overhang, like maybe we have something like this, and we still want the player to be able to catch this lip, but maybe, we shoot a line out and it just goes right here, but we want to shoot like multiple so that we do get this hit, right? So yeah, we're going to shoot a couple, and I'll let in the code, you can see you can pick how many you want, their density, how far they go, stuff like that. So then once we get this hit, if we don't get the hit, we're done, right? If there's nothing in front of us, there's nothing to mantle. But assuming we do get just at least one hit, then after that, we're going to do some calculations and figure out the up vector of this wall. So this wall could be pointed like this maybe, or it could even be like kind of underhang. We're going to get the up vector, and then we're going to come to the top of the wall, and we're going to shoot a downward cast like this. And hopefully we're going to get this top point. So that'll give us the height now, because now we can measure the distance from basically like the bottom of the capsule to the top of the wall. And then we can figure out how tall of a surface we're trying to mantle on. And then the last major thing we're going to do is we're also going to check if the capsule will even fit on top of here. So we're going to make another cast, or not a cast, sorry, we're going to make a geometry overlap test where we check, can this capsule fit where we intend it to go? And if all of these things are met, then we can perform the jump. And we're going to need to use these reference points to actually do that jump. So that's why I was saying that we need this stuff first. And when we perform the mantle, we also have to do a couple other checks, because we could be mantling over a surface like this where we probably need to do sort of the climb over it, or we could be having a short mantle where we just kind of step over it. You saw the difference between that tall mantle and the short mantle, and we're going to do a couple condition checks. So obviously the main one is the height. If it's something like this tall, obviously you're climbing over it and not just doing the quick vault. And if it's short, you just do the vault. Another test is going to be if we're falling. So say the character is falling down, even if they're technically like at the height where they could do the short vault, because they have that downward velocity, it's more realistic if we make them do the long vault or the tall vault. So they're going to fall and they're going to keep moving down, then catch the bottom and pull themselves up. Just a little more realistic than if they were falling and they just like pop up, which obviously would kill your wrists if you just try to grab the vault while you're like in the middle of the air. So it makes more sense that they kind of catch the wall and then slowly pull themselves up. So yeah, that's going to be what we're going to implement. You can do like whatever. So you could make like a variable number of vaults in between here if you wanted. Like if you wanted 3 vaults, if you wanted to have different animations, you want to have different conditions when they vault. Maybe you want the player to be able to grab the wall from super far away. It's pretty customizable. So I just want you to keep that in mind. Like if you were thinking, oh, I don't want 2 separate vault animations, then you can just edit that out of the system. It should be pretty easy. Everything is very compartmentalized, and you can really customize the conditions however you want, but the fundamental geometry tests I've made pretty robust. So now let's get into the code. All right, so the first thing we're going to do is create a bunch of helper variables that we're going to use. And we're also going to just make a condition. So if we are not actively walking and not crouching, or if we're not falling, then we're going to return false, because those are the only two movement modes that I'm deeming valid for mantling. But by all means, if you have another movement mode that makes sense to mantle out of, then add it to this condition. And then the next thing, our first geometry test. So we're going to check the front face, like I said in that diagram, and basically just check if there is any geometry that is directly in front of us that we can mantle to. So let's go through what we're doing here. So we're making a hit result for the front hit, and we're defining this check distance. So this is going to be the clamped value between basically cap radius plus 30 and mantle max distance. And the value is going to be velocity dot the forward vector. So the idea behind this code is that you have your character here, and they are going to have a distance they can check in front of them, like this. If the idea is that their velocity will control that. So if the character is moving very quickly to the right, say, like this, then we want to check very far ahead, because it will make sense that they can reach farther because they're going to travel that distance into the mantle. But say now we try to mantle and we're moving the opposite way, so maybe the velocity is this way, then maybe that distance is very small, because we can't really, we just have less effective range. I don't know if that makes complete sense, but you'll see what I mean more once we run this. But so basically we're dynamically sizing the range of the forward distance we can check based on the velocity. So that's that little thing. Then we're getting this vector for the start value of, or basically the start position of the line trace, because we're going to be casting out lines, and that's going to be equal to the location of the base, which I'm defining as basically the feet of the capsule. So you can see here that's the location, basically, and then you go down the capsule half height value. So the updated component location is at the center of the capsule, and then we go down 1/2 height to get to the feet, basically. So we're starting at the base, and we're adding the up vector, and then times max step height minus 1. So what is this referring to? So there is, if you're not familiar, there's a step height in Unreal Engine, which basically allows the character to automatically step up over very small obstacles. So like in this case, the character will just be walking and they'll just automatically go above this. They won't have to jump over this. I mean, this is actually kind of tall. It might be a little smaller. So the character's like this. They just, boom, they automatically go over it. So I want the mantle to work always if the obstacle is basically above the max step height. So basically, if there's an obstacle that is above the max step height, you can always mantle it. If I were to not do this, if I were to set this value arbitrarily to like 50, or I was to set it at the waist of the character, then there'd be this awkward range of obstacle heights where you can't mantle over them because they're too short, but you can't step up over them. So you just do a regular jump, which is awkward. So instead, we're going to make it so that you can always jump over you can always either mantle or step up on an obstacle. So that's why I'm doing that max step height minus 1. You'll see this as a recurring theme, just so that we can always make it over the obstacle. Now we're doing this for loop because we're going to iterate. Like I said, we're going to cast multiple rays out of the character to check, and we're just going to do something like this just to check. Obviously those will all be the same distance, and see if there's an obstacle there. So We're going to do a line trace to show that. But then, so this is just a debug line going from the front start, which is what we just declared up here, to the front start plus the forward vector times check distance. So that's the distance. This will get us basically this point here is line start, and this is line start plus forward vector times check distance, where the length of this line is the check distance. If this, basically, because it's in a loop, right, we just want to find the first valid hit. So if we get a hit for this line trace, we're going to break the loop. Otherwise, we're going to increment by this factor, which all this is saying is that we're going to basically increment the height of the start condition of the line up by a factor of like this factor. I don't know how else to say it, but basically this will allow us to get 5 line traces that all fit somewhere between the lowest line trace, which is at the max step height, and the head of the capsule. So, if you want to increase the fidelity of this, maybe you have really thin geometry that you want the player to mantle on, like something like this. And I actually do have this in my demo where like sometimes line traces will go like this, and you want to be able to get all that fidelity. Just increase this number to say like 10 and increase this to 9 to just buff up those the number of line traces. So then after this for loop runs, we're going to see if we got any hits. So we can do that by just saying if there was no valid blocking hit, return false. Because notice we're using the same hit result for all these line traces, but just the last one will either be valid because we broke out of the loop when we got a valid hit, or none of them were valid. And so we're just making sure, did we hit anything? And if we didn't, just return false, get out of this whole function because mantling isn't possible. Now, once we have a valid wall, we're going to take the cosine of the wall steepness angle. So, this is going to be a little bit of like vector math, a lot of vector math, just a lot of dot products. So if you don't know, the dot product is an operation that is essentially finding the cosine between two vectors. So we're taking the normal, which is going to be, so like we have a surface here, that normal vector is going to be the vector that points directly out of the face. So in that case, it's going to directly point right out at the player. So it's going to look something like this. And we're dotting that with the up vector. So this symbol, this is typically the OR, or the bitwise OR, but there's an operator overload for it to be the dot product. So sorry if you guys don't, you're not familiar with some of this stuff, but this performs a dot product between these two vectors. So we're storing that. That is equivalent to the value of the cosine of the wall steepness angle. So what does this mean? Basically, this number can be from 0 to or from -1 to 1. 0 means that the wall is straight up and down, whereas like if it was say like 0.5 or something, or if it was like say 0.7, then the wall would be at like a 45-degree angle like this. And if it was say -0.7, then the wall might be like an underhang like this. And the reason why we're checking these two conditions is because, or just this one condition, is because we have a limit to how steep or how shallow the wall can be where the player can't actually mantle it. So like something like this, the player couldn't mantle this because, they'd have to kind of tip over or something. I don't know what they'd have to do, but this wouldn't be a valid mantle. This, maybe we could say this is a valid mantle, but we're mostly just clamping it to a fixed angle. So then now that we have that steepness angle, we're going to check the absolute value of the steepness angle, and if that's greater than cosine WSA, what is that? We define that up here as a helper. That is the cosine of mantle min wall steepness angle. So basically, we're just saying what is the minimum steepness that we're still going to tolerate and be possible. Once it gets steeper than that, we're going to say no. Actually, I guess, should that be max? I guess the idea here was steepness. When it's completely steep, it's like perfectly 90 degrees. So if it was, say, only 60 degrees, that's kind of shallow. So what's the minimum steepness we're going to allow? And I set that as a parameter. I believe I have that as 75. So that's something maybe like this. Whoops, that's if the wall is at a 75-degree angle, you can still make it, but once it gets something like this other line, like 45 degrees, then it's way too shallow to mantle over. So if this condition is not met, we're comparing the cosines here. That's just a way to check if this angle is greater than this angle, or this other dot product that I'll explain. So if either of those are met, then we're returning false. We're getting out of here. What this other one is saying is we're dotting the forward vector with the normal vector of the wall. So now let me erase some of this for a second, and let's go to a top-down view. So if you're looking on top, and here's the player, and here's, say, the wall they're trying to mantle up, they don't have to mantle straight on, obviously, right? I mean, if every wall had to be perfectly straight, and the player had to like perfectly align themselves like this way to go straight into it, then that'd be really hard. We need to be able to like, come in at an angle and still make it over, right? But, it can't be so steep of an angle. We can't have them trying to come into a wall like this and mantle in this direction. We do want to have like a sanity check so that they have to be at least pointing sort of in the direction of the wall to be able to mantle over it. So that's the next check we're doing. Erase this. I should say, so that normal vector on the wall, in this mode, in this view, it would look like this, right? It would be coming perpendicular out of the wall. That's not very perpendicular, but perpendicular out of the wall. And the player has a forward vector, say something like this. And so we're dotting these two vectors, except we're dotting the minus of the hit normal, because if you dot vectors pointing in the opposite direction, it'll be a negative number. So if we minus that, we're going to get this vector. And if we dot this vector with this vector, then the closer they are to being perfectly aligned, so like if the player is pointing this way and the wall is pointing perfectly back at them, which is like a perfect mantle, then that will become 1 when you dot it like this. The farther they are from being aligned, so say the character is trying to climb up like a really slanted wall, like they're pointing this way and the wall's like this, that's approaching 0. So basically we want this number to be as large as possible. So we're only basically, if this is less than a certain value, then we return false. What is that value? It's another helper redefined cosine MMAA, which was mantle max alignment angle. So I'm calling that alignment. Sorry, it's kind of dense, but assuming both of these conditions are valid, then we didn't return false, so we're moving on, and then we're doing a point. We're gonna draw a point here to indicate that this is the point in the wall, which is going to be the location of this hit to show where we got a valid hit. Okay, so let's go to the editor and see this, because I want to put this in chunks so that you can see what's actually happening, since it might be kind of frustrating to like do all of this and not be able to see what you're actually dealing with. So now, we have this nice debug lines. We're going to see what geometry we're hitting. It'll build up probably hopefully more intuition of what we're doing, and you'll be able to get some progress. So let's see that. Oh shoot, I forgot that, you have to always return a valid control path. So I'll return true actually here. I just didn't have a return statement, but this is a boolean and it needs to have a return. Okay, so now you can see I come up to this wall and I press space, and you can see that we didn't jump, which means that's good, because since we returned true at the end of that function, we had a valid mantle, so we canceled the jump performance. And you can see that dot there, that's indicating that we successfully found an object. And so you can see when I do it and there's no objects, you can see we get all these lines, and those lines are all the traces going from the head to the feet, and you can see they're not hitting anything. And then the last important thing you can see is the speed. So if I'm just standing still and I do that, it's only a very short distance ahead. But if I'm running and I do that, you can see a very long distance for these lines. And the idea is that you can increase the range of your mantle if you're like going in that direction, because you have that speed. So I'll just come around and you can see where the hits are. If I'm pointing in different directions. So yeah, now hopefully that should give you an idea of what that's looking like, and we'll move on to our next check, which is going to be, we're going to check that top surface. So we've checked this surface, and now we're going to check the top surface. Actually, I guess one thing I should demonstrate is that making sure that cosine worked. So if I come back into the level editor and say I make this a little steeper like this is definitely now worse or greater or less steepness than 90 degrees. This is probably maybe, I don't know, 60 or something. And so you can see it fails. The trace hit successfully, so there was a dot in there. I don't know why you can't see it very easily, but there's a dot there, but the cosine of the angle was less than 90, or it wasn't 90. So the wall is just too shallow and the mantle just can't be performed. So let's go back to the code. Actually, I won't say that change yet. Okay. So the next thing is checking that top surface. And it's a pretty big portion. So I like to bring my macro calls like this, like to the lowest level indentation, so that I don't, like, when I'm reading it, I can easily tell that it's not code. It's just debug stuff. So, okay, what are we doing here? So now we actually are declaring an array of height hits. I'm calling it, we're checking the height, which is going to be, casting downward and finding the top of that surface. So we have height hits, and then we have a surface hit. So these are two separate things. The first, and then we make these variables. So we have wall up, which is going to be the vector plane projection of the up vector on the front hit normal. So if you don't know any vector math, this could be kind of tricky to understand. But so let me try my best to explain this real quick. So basically you have, say, a plane. So here's a plane, and you have the plane as a normal vector. Normal vector looks something like this, pointing directly perpendicular and out of the plane. And then maybe we have we have the world up vector. Oops. So the world up vector, I keep drawing these little dots. Whatever. So the world up vector is just obviously straight up. There we go. And we project this vector onto this plane. So what that looks like is it basically gets a copy of the vector, but the vector only can lie in the plane. So in this case, it would probably look something like this, where the vector is perfectly on the surface of the plane, but it's maintained the most like upwardness it can be in the plane. It's not a great definition, I guess, but I guess you hopefully kind of get the idea. It's similar. It's kind of the opposite of projecting a vector onto another vector. So when you project a vector onto, say, another vector, you're just getting the component along that vector. Here, we're actually removing all components of the vector that are along the normal of the vector, and that gives us a vector that's only in this plane. So the reason we're doing this is because we want the quote-unquote wall up vector. So we want the vector that is perfectly going upward along the wall. So if we go back to our 2D case, here's the character, here's a side view, here's the wall. In this case, the normal vector looks like this, pointing straight out. And if we take the world up vector, I'll draw that here in blue. This is the world up vector. And if we project that onto the surface normal of this normal here, it's just going to be the same thing, right? It's literally just going to be the same thing because this world up vector already sits on this plane right here, right? Because they're both perfectly straight up. So that's easy. If it was not the case, so say this angle was slanted. So maybe you have a wall that looks like this, and this is still a mantleable wall, or maybe more realistically, I'll draw it the other way. You have a wall like this, and this is, there's no reason why the player can't mantle this, right? But notice, if you have your normal vector now pointing like this, then we want to get to, so our goal is to get to this point. Our goal is to get the point right at the tip of the edge so that that's where the player can grab. But if we treated this like a vertical wall, we would think that the point the player can grab is up here, perfectly over the hit point. And especially if we're casting our rays down here, we might think that the character needs to grab here, and then when we move them to this point, we clip into this geometry. So instead, we project the world up vector onto the plane of the wall we just hit, and that gets us a vector that looks like this. So it's going to go along the edge of this wall, perfectly up the wall, and that will allow us to get the point that's right on the tip of the wall, which is what we want. So, okay, so that was the wall up vector. Now we're just going to get the wall cosine, which is the angle that created. So that's basically the cosine of the angle that's between these two vectors. So the world up, actually I should have drawn that in blue, the world up and the cosine and the wall up, basically. Then we're going to get the wall sine, which is the opposite of that. Hopefully you guys, everyone's familiar with sine and cosine. And then we're going to get the trace start. So similar to here where we did the front start, we're just going to build this trace start, which is a big vector that's going to be where we start the trace. So that's going to be the front hit location. So piggybacking off that previous point we found, that's going to be like this point where we hit the wall, plus the forward vector. So we're going to go actually in by one forward vector, by a magnitude of 1, times the wall up, which is that vector we just found, pointing up the wall here, times, and then the magnitude of that vector is going to be max height minus basically min height, right? Because that's the shortest value that we can mantle. All of that divided by wall sine. So basically, I guess I won't try to explain all of this, but basically the goal is to get us to the point that is sort of right up this line and the highest up that we're allowed to mantle. So because we're referencing that max height, the highest allowable point we could possibly mantle, and getting us right up to that point. And then we're going to cast a ray back down through here to check the surface. The reason why I'm adding a small forward vector component is because this surface point here is going to be right on the edge of the wall. So technically a vector casted straight down along the surface, it might not hit because it's like literally pixel perfect on that edge. So I'm going in by a value of forward vector, just magnitude of 1, so that our cast is going to be slightly inward, so that we don't risk not actually clipping the geometry. So we're going to draw that line so we can see that, and then we're going to actually perform the cast. And if the cast didn't hit anything, then we're going to return false, because basically if there was nothing there for some reason, then there's nothing to mantle on, so we're going to return false. And notice we're doing line trace by multi by profile. So the reason I'm choosing multi is because there could be like underclings or overhangs or who knows what that you want to get over. So I'm just making this as bulletproof as possible. So say for example you had some, I don't know why, but some geometry that look like this. Or maybe, maybe, let me zoom out here. Maybe the character has like a space they can fit under. So here's the capsule, and then there's a place to mantle, and then there's a place above that, and you want to just fit like right between there. But if we start this line trace, and maybe we started in penetration and come down here and test it, if we just take the first hit, which will be like this thing we just penetrated, then we don't get anything. But there was a valid place to mantle. So we're going to do multi-trace so that we can get these collision points in multiple locations. And then we can see, oh, this one's valid. So we want to do a multi-test just to make sure our system is absolutely bulletproof. And that's why we made that array of height hits and the trace location. And basically, all we're going to do is loop through the hit results, and if we find the first valid blocking hit, that's going to be our surface hit. So if we started in geometry, this is going to be an invalid hit, but it's still going to be a hit. The next valid blocking hit we come across, that's going to be the one we want. That's going to be the one we can mantle to. So we're going to grab that, put it into a surface hit, and break. Then, similar to our last approach, we're going to check, is this surface hit a valid blocking hit? Because this code might never have run. It might never have found any valid hits. And if that's the case, return false. And it's also the case if the surface hit normal dot the up vector is less than cosine MMSA, which is max mantle surface angle. So what does this mean? Well, there's also a limit to the angle you can mantle on. So say that the top of the slope you wanted to mantle on was something like this. Well, that's pushing it. Okay, maybe something like this. That we definitely can't mantle onto, right? Like there's nothing to stand on. So if you just naively didn't include like this, then you might say, oh, okay, there's a valid point right here. There's a valid point right here. Let's go ahead and perform the mantle. But, what can the player grab there? What can the player stand on? There's really nothing. So we want to make sure that the angle or the steepness of the surface is also shallow enough. And again, we're going to do that with normal vectors and vector math. So we're going to get the dot product between the surface normal and the world up vector. And the idea here is that, again, regular dot product notation, if the dot products are similar enough, which means they're approaching 1, so 1 would be both dot products are exactly aligned, then that's good. If they're if the surface was very steep, however, then the dot products would be very unaligned, and that would cause it to be like 0, say, or closer to 0. And so if it's less than this minimum surface angle, then we're just going to return false. After all that is done, so after all these checks are performed, we know that we do have a valid surface. So we're going to go ahead and calculate the height of that surface, which is going to be the surface location minus base location dotted with the up vector. So another thing that dot products technically do is they get the component of a vector on another vector. They're not doing multiple things, they're just different ways to interpret them. So if you have, say, so say here's the capsule, right? Let me undo some of this. So here's the capsule. Here is the, say this is the slope. And you've just got this point right here that you found. Oops. And we want to check how high that is from the base of the capsule, because everything's going to be in reference to the base. So we're going to do surface location minus base location. So that's going to be a vector that basically looks like this. It's going to be a vector that points from here to here. And we can't just take the distance of this vector. That doesn't give us the height because this is at an angle, so this is going to be way larger than what we want. But when we dot it with the world up vector, which remember is just this vector, we're actually, the value of this dot product can be interpreted as the component of this vector on the world up vector. So what would that look like? If we just take a line over here, it's going to be this distance. So however far that distance is, that's the height of the mantle. And as you can see, that does achieve the desired effect. That's basically how tall the obstacle is that the player is trying to mantle over from the base. Then we're going to log that to the screen. We're going to draw a blue point on that surface. And then we're just going to do a sanity check and make sure that the height is not greater than the max height. Technically, it shouldn't be because we only cast this line from the highest possible valid point. But we're just going to do this just to make extra sure. It doesn't cost anything really. So let's jump into the editor now and see what this looks like. Okay, so you can see when I try to jump, we get the red dot where the surface hit, and then this is an especially good example because it's showcasing that angle. We get the angled orange line that is perfectly in line with the wall, and we get that blue dot, which is right on the tip of that ledge. So I'll come over here. You can see other examples of this. Pushing the limits, yeah, that's the undercling version kind of. You can even see, so here's another, I should have showed this last time. So here you can see that we're doing multiple traces because the initial traces didn't hit. But you can see that that last one did hit, and this is a good example of something that you might not think to account for this when you're first making the mantle, because you might not be designing for this kind of an undercling, but obviously this is something that your level designer or you might want to put in the game, and you do need to account for all these different situations. I guess I'll also maybe show an example really quick of, I don't know if I have an example. I don't think I have an example of like making the geometry for the surface angle. So I'm going to show this. Put this right here. So if you have varying surface height, let's test this to make sure this works. This should not work, right? And as you can see, it doesn't. So I can't mantle on this. But as soon as I decrease the angle of this to a certain acceptable value, I think that should definitely work. So let's just make sure this works. And as you can see, it validated the height because this angle is not too steep. So that's all we wanted. So let's jump back in and finish the remaining checks. So the last check we're going to do is clearance. This is just going to make sure there's room for the capsule above. Here, I'll show this diagram again. So there's basically, we're just going to do a geometry test above the mantle height to make sure that there's room for a capsule to fit there before we try to move on to that place. Obviously, if we might get a point, like say there was a something like this, there was a space to mantle, but there was a big obstacle right above it. This is no good. Obviously, the character cannot mantle into here because there's no space. There's just this little gap. So we need to do basically a cast of a geometry overlap test with a capsule that's the same exact size as the player and see if that interferes with anything. So that's what I'm calling checking for clearance. So we have to do a couple setup first. So we have to get the surface cosine, which is again, so that's going to be the dot product of the up vector and the surface normal to check that steepness or that, I guess, that angle of the surface they just are trying to mantle onto, and as well as the surface sine, which is going to be again like we calculated the sine up here. It's going to be the square root of 1 minus cosine. That's just Pythagorean theorem. And then we're going to get the clearance capsule location. So this is going to be combining all of these into one. So we're going to get the surface hit location, which is that first point. So we're going to remake this situation real quick. So that first point, say that looks like something right here. So we're going to get that point. Then we're going to add a forward vector so that we go in a little bit more. Sorry, times capsule radius. So we're actually going to go in by a factor of capsule radius because we want the character to be wholly on this surface. So if we put them right there, they're going to be halfway on, but we want to go another factor of capsule radius into the geometry. So that's like a full capsule standing on there. So times capsule radius, then plus the up vector times this weird factor. So what this is accounting for is, well, first it's just accounting for the capsule half height. So the capsule location is always measured from the center. So what this really looks like is it would look like this right now. But then we want to add half of the capsule's height to get it to be standing on here. But then we also have this other weird factor, which is capsule radius times 2 times the surface line. All this is saying is we're going to go up a factor because of the angle of the surface we're trying to mantle onto. So what that means, like say the surface was angled like this, then if we just perform the test, like say we just don't account for this and we perform the test just exactly above the height, we might be like here and we think, oh, we can't mantle, right? Because we're intersecting with the surface. But in reality, we could mantle and be standing right here. So we need to account for the slope of the surface we're trying to get onto. So that's what we're doing with that surface cosine stuff. That's what this whole term is for. After that, we're going to make the capsule shape, which is like a weird parameter you need to do overlap tests. So we're just making a capsule with their syntax out of capsule radius and capsule half height. And then we are saying, here's the test. So if, overlap any test by profile, and the any keyword means basically this doesn't even have a like hit result. This is just a Boolean. This is just yes, no. So if we hit anything with this capsule, then just tell us whether we hit it or not, but we don't even need any data on it. And that's just a little bit faster, obviously. And so we're just, passing in 0 rotation because currently in the iteration, the capsule's not rotating really any way that's important. And we're passing in that capsule shape, and that just defines that. I should have mentioned this. I should have mentioned this earlier. The params here, we made this variable up at the top with auto params. And then we called zippy character owner get ignore character params. If you've been following along, this is just a nice little function I make in all my projects, which really easily gives you a collision query params test struct that already ignores all of the character stuff. So usually when you're doing something like, you're making a line trace for a gun, right? You don't want to intersect with the player itself. You don't want the player to shoot themselves, or you don't want the player to mantle themselves. And so you just get this ignore character params, and then you pass this into any of your line traces, and it won't touch that geometry. So where were we? So we're ignoring the character completely when we do that test. And if that was the case, then if that's not the case, so if it collided with anything, then we return false, right? And we also are gonna we're going to show that capsule in red, indicating that it was a bad hit. There was geometry in the way. And otherwise, we're going to proceed and we're going to show a green capsule to show that everything worked, and we can move on to there, and the surface is valid. So let's hop in the editor. And so you can see in the editor here, I just set up this geometry here that clearly obstructs the capsule if I tried to mantle onto this. And you can see it doesn't work. We just default into a jump, and there's that red collision showing that the capsule collide with something if it were to go up there. Whereas something where there's space, you can see the capsule's green, meaning we can validly get up there, and you can see very clearly where we'd end up. So also testing with a surface angle, you can see I add this little space. You can see I move the capsule up higher to account for the surface. And yeah, it's more visibly noticeable here that if the capsule was right up against the flat surface, it would collide. But here we're just adjusting for that um, because of the slant of the surface we're trying to mantle onto. All right, so at this point we have the go-ahead. All the conditions were met. We can perform the mantle. Everything should work just fine. So yeah, so now we have the go-ahead. We can perform the mantle. And so the first thing that we need to do is mantle selection. So we need to check, do we want to do a tall mantle or a short mantle? And the way we're going to do this is using these helper functions that we have to go implement. But basically, there's a couple cases. So if we are walking and the height is greater than the capsule half height times 2. So basically, if the ledge is above the head of the character, then we want to do a tall mantle. And the other case where we do a tall mantle is if we're falling and if the velocity is if the velocity dot the up vector is less than 0. So that just means if the velocity is pointing anywhere downward. So if we have any down velocity, and if the get world overlap test profile any of the tall mantle target. So sorry, what that means is basically if there's no collision between the tall mantle's target location and the geometry, then we can move there. So then if that's true, we're going to perform the tall mantle. So the reason why I do this overlap test is basically say that here's the ledge you want to grab onto, and here's your capsule. So you're falling and you want to perform a tall mantle, but to perform a tall mantle, you need to get into this position. You need to actually come down all the way to here and then lift yourself up. But say this geometry is not long enough or tall enough for a tall mantle, so you could try to mantle onto a very short, you could be falling and still want to mantle onto a very short overhang. So like you come down here, you press mantle right here. If you press mantle right here, then even though you're falling onto this ledge, you should still perform a short mantle because you can't actually move down into this floor to perform a tall mantle. So we just want to make sure there's room to perform the tall mantle to get all the way down here and then lift yourself up. So these are the only cases where we perform a tall mantle. Everything else will be a short mantle. And, customize this to however you want your mantle to work, but these are just the ways that I'm selecting. But this is like an example. This is a region of the code where you want to change this to be your mantle selection. Maybe you have 3 mantles. Maybe you have 5, 10. I don't know. Partition these off and section off how you're going to select your mantle. And then I'm also just going to do a nice log or capsule debug trace showing the yellow capsule, which is going to show where we are trying to transition to, and the red capsule showing where we currently are. So there's this idea of the transition I haven't explained yet. So let me erase this. So here is your wall, and here's your capsule. And the capsule might be moving. Maybe they're right here, and they hit mantle. Okay, we've checked, we've done all the traces, we're good to go. We should be able to mantle up to here. But we're going to use root motion. So root motion is when you use an animation to control the movement of the capsule. But root motion is very picky. It only ever operates the same each time. And so for our root motion animation to work, we need to be in this very specific position. We need to be right up under the wall, and then the character will reach their hands out and grab this edge. And it's all very precise, and they'll pull themselves up to this very precise location. So given that we could be anywhere in this region and the mantle will still work, we need a way to get there. And that's going to be where we use root motion. So we're going to have this transition phase where we transition into that point that we want to then perform the mantle out of. And that's going to be done with root motion source. So that's what that transition target is. So let's real quick write the get mantle start location, which is the end result of the transition. This is where we need to be. This is this position that we need to be. So that's the start location of the actual mantle. So let's implement that. That's this function we made right here. So it's going to look something like this. Basically, more dot product stuff. I guess I won't explain all this, but just we are working our way backwards from this point on the wall to this point right here. Yeah, I think this is just going to be too much to go into all the details of like where I'm using the cosine and the cross products and stuff, but basically I'm just starting from the surface hit, which was that point, and then I'm working my way back in a series of movements. So like, I'll just go real quick. So this one is going backward to here, and then this one is going this is going along the wall. So if I go to top down view, whoops, try this as fast as I can. Basically, here is our say here is our edge hit, because maybe we're facing like this, but we're actually going to go a little bit backward to like say right here, because I've noticed in testing it looks really odd if the character mantles by like jumping all the way over here, when in reality the wall is really right up against them. So we are going along the edge tangent to kind of go back to the capsule a little bit. Then this up vector times capsule half height, so that is going to be moving the mantle start to be, say, basically up the capsule half height. So it's going to go from the capsule traditionally being right here to right here. So I should just draw that with the arrow. Then we go down the down distance, which is that this depends on what type of mantle we're in. So if we're in a tall mantle, that's 2 times the capsule half height. And if we're in a short mantle, that's that max step height minus 1. So we're going to go down some distance. This would be like, for example, the tall mantle. And then we go up. Oh no, sorry. We did that line, and then we go front hit normal times the cosine steepest angle times the down distance. So that line is going to move us away or towards the edge depending on the edge steepness. So this was another kind of weird thing you might not think to take account for. But so if I erase all of this, now say the wall was something like this. Obviously we can't move the capsule into here to form the mantle. We need to be like out here. So this just bumps us out using the surface or using the normal of the front face to an appropriate valid region that we can then transition to. So all of this combined is going to give us that starting location, that perfect location that we can then perform the mantle from. And it all depend too on whether we are in a tall mantle or short mantle. And yeah, we need to pass in those hit values, right? So we can get like their normals and stuff. So once we get all of that, we can cache these values for what the short mantle target and the tall mantle target would be. So like this will be the tall mantle target. This will be like something like the short mantle target. And those are the places that we can play the root motion animations and like get that perfectly lined up in sync result from here to here or from here to here. So yeah, we get those, then we do the mantle selection, and then we just set the transition target to be whatever mantle target we selected. So if it was a tall mantle, then we select the tall mantle target, and if it was a short mantle, we select the short mantle target. Then we're gonna draw in yellow a capsule showing the transition target, and in red the current location. So let's go into the editor again, just so you can visualize this before we actually start doing the animation stuff. Okay, so I press space. You can see that red capsule right there is where we're currently standing. The yellow capsule is where we're going to move to for the transition, and the green capsule is the final location. So you can see this indicates that clearly we're doing a short mantle, right? Because the yellow capsule is really high up. So we're going to be just stooping really low to just like pop our hands over that height, because this height of this surface right here is like the absolute maximum height you can still short mantle. So you might not like that. You might think, oh, this is kind of tall. Maybe you want a medium mantle. I don't know what you want, but that's the maximum possible height. If I go to here, you can see, well, I forgot to put that geometry there. If I go to here, you can see the transition, that yellow capsule, the transition target is a lot closer to where we currently are. That's because this is a tall mantle. So this, we're going to reach our arms all the way up there. We're going to grab the lip of that edge and pull ourselves all the way up. So this is sort of the minimum height, or this is the regular height that you'd perform a tall mantle on. And, I'll just show in other aspects, like if you come up to this wall, you can see, where we were. And you can see in that case, I should have made the length longer, but you can see in the case of this wall, you can see that the red capsule is actually above the yellow capsule, so we'll move down a little bit before we then pull ourselves up. And that's kind of just a fakey way of like making it feel a little more physics-based, because you're falling against the wall, and you're going to fall against the wall a little bit more, and then pull yourself up once you reach that bottom point and your hands are on the edge and you're max extended, and then you're going to lift yourself up. So now let's do the animation stuff. Okay, so from here on out, we've selected the mantle. We've shown that we can mantle to this location. We have which one we want. We have all the data we need. Now we are going to do the transition and cue the actual montage. So again, like I said, we can't just immediately play the animation montage, because what if we're like, say, right here, and then we mantle like this, right? That would look stupid. What if we're like, I don't know, we're still far away. We just mantle up here, but we're not actually over it. So we need to transition the capsule to the ideal location and then perform the montage. And we're going to do that through root motion. So what is root motion? Root motion source. So root motion source. So, okay, everything is root motion source, but non-animation root motion sources are basically ways that you can drive capsule movement with root motion, but it doesn't have to be through a montage or through an animation. It's really just another way to move the capsule. It's not like anything that special, but it's nice because you make a root motion source, like it's a whole object. You make this object and you make it do your movement, and then you just remove it. So it's not like you have to spend all this time making a new movement mode or a new like permanent mechanic. It's something you just add and it goes away in a second. So that's the nice part, is that it's good for something like a transition, because you don't have to waste all the bandwidth and all the effort of creating like mantle transition movement mode and slide transition movement mode. You don't want to make transition movement modes for every type of movement in your game. That's just really clunky. It's hard to get at what you're really trying to do. So we just add this really quick temporary transition and perform it, and then when we're done, we pop it off, and it's like it never even existed. So, okay, what are we actually doing? So first, we are getting some values here to calculate like how far we are away, and this is that speed. The up speed is how fast we're going in the up direction. Here, we're actually setting the transition cued montage speed. I'll explain first. I'll explain this in a second, but first what we're doing is this transmission RMS. This is a root motion source. So if I go here, this is a shared pointer to a root motion source move to force. So root motion sources, there is a base class, right? And you can make your own custom root motion source that will drive movement, right? But Unreal Engine provided a couple default, like kind of elemental or like the most common use case root motion sources, and one of them is just move to force, and that'll just move the character to a location over a fixed duration, and that's just all it does. So it's perfect for us, right? We just want to move to this location. We just want to move in a like short duration that we can control, and we want to have precise control over where we're going from and where we're going to, and then we remove that and the transition's over. So that's a transition root motion source. That's a root motion source move to force. So we're going to reset that, but this isn't actually resetting the transition root motion source. This is resetting the shared pointer because I'm using the dot here instead of the arrow. So this is deleting the previous root motion source from the shared pointer. Then we're going to make a new shared F root motion source move to force struct. So this is going to make a whole new object for us to reuse. We're going to set the accumulation mode to override because we don't want it to accumulate with any other root motion sources if there were any. Just want to do this if like this is supposed to be the only thing that is playing. Then we're going to set the duration to be this, which is going to be clamp the transition distance divided by 500, and then we're going to clamp it between 0.1 and 0.25. So what is this doing? So you can transition into a montage from a couple different ways. You can be far away, maybe you have a lot of velocity, you can be really close, and so if you're really close, if we just had this transition distance be a fixed time, like just say 0.2, then this would be a little bit immersion breaking, because say you're right here, you're right already exactly where you need to be, and you press that button, then you're going to still take like 0.2 seconds, and then you're going to perform the mantle. So basically all we're doing here is we're dynamically setting the duration of the transition based on how close we are. So if we're really far away, it'll take longer to get there and transition up. And that's setting the duration of how long this transition will take. I'm just logging the duration. And then we're setting the start location just to be the location of the capsule, obviously, because that's where we are. And the target location is just that transition target. Now we're actually going to apply that transition root motion source to the movement component. So a couple things here. Velocity is going to be set to 0. This is because velocity is actually what's used to affect the capsule position. So the root motion source isn't updating its position, it's updating its velocity, which then it gets applied through the physics function. So we want to zero that out first. Then we're going to set the movement mode to flying. And if you watch my previous video, I was just talking about how you need to be in flying movement mode to perform root motion in like 3 dimensions. So if you're still in walking, if you're in the walking movement mode and you try to apply root motion, you'll actually you won't move anywhere in the Z axis. You'll only move left, like left and right, forward and backward, because you're still getting gravity applied to you. So we need to set the movement mode to flying, and then we just apply root motion source, and we use that root motion source we built, and we get back this root motion source ID, which I also have. It's just an integer, and we're going to save that away because we're going to need that later. Next, after we've applied the transition, we're going to queue up the, we're going to, basically play some animations, and also queue up a montage for the, basically when we're done with the transition, what montage we're going to play to then actually perform the mantle. Because remember, this isn't performing the mantle, this is just getting us into position. So if we're a tall mantle, then we're going to set the transition queued montage to the tall mantle montage. Obviously, if we're a short mantle, we're going to set that to short mantle montage. And then we're going to play the transition tall mantle montage. So this is not a root motion montage. This is just a pure animation. The reason we're adding this line, and it'll make way more sense when we're in the editor, but we actually have to play a transition so that the character can get into position to perform the mantle. Not just like physically, like their capsule has to be in the right position, but animation wise, this will move their arms to be in the right position to grab the wall and then start the mantle so everything looks smooth. Typically this is done with blending, but we don't want to blend a root motion montage because that's going to provide a bunch of other difficulties. So we're kind of doing custom blending basically, which it kind of stinks. I wish there maybe was a better way to do this. Maybe there probably is, who knows, but this was what I found the most reliable way. And The play rate is going to be, you see, 1 over transition root motion source duration. So what that's going to do is I made this transition montage be exactly 1 second, so that now we can dynamically scale the duration of that montage to make it so that the character will always move into the correct position over the course of the transition duration. So you'll see it just ends up working out pretty crisp. And then if we're a server, we're also going to toggle this proxy tall mantle value, and that's going to allow the animation to play on the client, remote proxies, so that they can stay up to sync with the animations. And we'll actually look at how this is being implemented later. But we do the same thing down here, but just with the short mantle montage. And then going back up here, so now you kind of get what I mean by the queued montage we're about to play. So we also set the speed of this montage, and that speed is based on the up speed. So this might seem unintuitive at first, but the idea here is that if the character is moving up very fast, we're going to play that mantle montage fast, because they're moving up, they have a up velocity, maybe they just jumped up and then they mantle, so they're going to mantle very quickly. If they're falling, on the opposite of that, if they're falling down, the mantle is going to play very slowly, because the idea is like they're completely killing all their velocity, so they have to like come to a stop and then pull themselves up slowly. Whereas if they already have a ton of vertical velocity upward, they're just going to play the mantle very quickly and just immediately pop up here and be good. So this is another polish feature I added. Basically, it's just I think it's a cool little polish that makes the mantle feel way more reactive and gives way more feedback. You actually feel like you just fell a large distance and actually had to grab onto this ledge, versus we're just playing a pre-canned animation every single time. So this just adds a little bit more game feel to it. So yeah, that is everything we need to do in the tri-mantle. So that was pretty grueling, but we're almost done. So let's do a couple more things in the code before we hop into the editor and check this all out. So first, we are going to come right under the update, or we're going to fill out this update character state after movement. So that is going to look like this. So what we're doing here is we are doing a couple checks. So the first check is we're saying if there was no anim root motion, and we previously had anim root motion, and the movement mode is flying, then we're going to set movement mode back to walking. So this is piggybacking off what we did previously, but we're actually making an updated version of it. So all this is saying is if we're playing an anim root motion montage and we just ended it, then we need to go back to walking, because like I said, we had to be in the flying movement mode, but after the mantle's finished, we want to be back to walking. Obviously, that if it's not the case, then that'll cause problems. So we set movement mode to walking here. Ending, you can see I log ending anim root motion. Then another check we do is we say if, and then we get the root motion source by ID, and here's where we use that transition ID. So if that's valid, meaning that just exists, it was a valid root motion source, and the status.has flag finished, this means this is the frame that the transition just ended. So this will occur on some frame the transition just ended, and we want to remove that motion source, because this doesn't, you don't have to remove it manually, but I'm removing it here, and then we are toggling this safe transition ended or transition finished, and then also we're just updating this had anim root motion value so that we can correctly use it in the next frame. Okay, so what's the logic behind this? So the reason why I'm making this transition finished variable is, and this took me forever to figure out, because the character movement component can sometimes just be really dense and annoying to work with, but basically it's a pipeline order problem. So if I go to the I won't bore you too much with the details, but if I go to the usage of this, believe it's right here, yes. So this is perform, we are in the character movement component source code. We're in perform movement. So if you look, I actually made a, where is it? Here, I made a little notes of what the actual pipeline is. So first we just call some stuff we don't need to care about. We clean up root motion sources here. So if you didn't get rid of yours manually, it would be cleaned up here. Then we apply accumulative forces. Then we update character state before movement. So this is that call to that function we made. We know what this does. We handle pending launches. We clear forces. Here is where we update the root motion. Here's where we update it. We apply it to the velocity. And it's not directly applied to the position, as you can see I said. It's applied to the velocity, and then a velocity applies it through the physics function. Then we clear jump input. Then we actually start new physics. This is where the move happens, right? Remember, this is where all of the movement logic of the movement mode takes place. Then we update character state after movement. Then we call physics rotation. Then we apply root motion to rotation. Then we call on movement updated. Then we just like handle some net stuff and stuff like that. So previously we had handled like ending animations and whatnot through on movement updated, and that's what I was gonna do because that makes sense. But actually we want to do it in this update character state after movement, because when root motion gets applied, it gets consumed as well. So it's kind of a weird thing, but so the value of has anim root motion is only valid before we actually apply the root motion. After we apply it, this gets consumed and it doesn't think it has anim root motion, as well as a couple other problems. As like stuff like this also has problems. So we need to call this first so that we get the valid root motion data before it gets consumed in this function call. And then we need to cache that in the transition finished value. The reason why I'm caching this instead of being able to directly work with this is that I was going to try to directly test this case in the update character state before movement, but remember the cleanup happens right before that. So I was not able to test this condition because my root motion source was automatically being cleaned up. I wasn't able to check it in time. It had been already removed by the system, and so I was never able to get a event trigger, and I was never able to get that like trigger of when the root motion source just finished, because it finishes right here, it finishes on the application, and then it gets cleared right here. So it finishes the cycle, and then it gets cleaned up before I can ever check it. So that's why I need to do this stuff in update character state after movement, so that I can get the value before it gets consumed, right? And before it gets cleaned up by like the perform movement function. So yeah, that was so frustrating to figure out, because I was like, it's, everything should be working, but I just didn't realize the order of the functions in the source code was preventing me from ever reading this value. So yeah, I just had to rant there about that so that you guys knew how long that took me. But anyway, so after we check that, we cache this value, saved transition finished, and that means the transition was finished. So then we can go up to update character state before movement, and now we have a valid Boolean indicating when the transition was finished. So we're going to obviously use that to play our queued anim montage. So if that transition finish is true, then we're going to log, we finished the transition, finished the root motion source. We're going to get rid of all these logs at the end. But then if we have a valid transition queued montage, this is a pointer to a root motion montage. So if that's valid, then we're going to set the move mode to flying. We're going to play the montage. We're going to clear out the queued montage speed, and we're going to clear out the queued montage pointer. And yeah, this will play our root motion. This is finally where the mantle montage is actually being played. This is the mantle itself, just this little tiny chunk. So it took forever to get there, but this is what's playing the mantle. Otherwise, if there's no valid cued montage, just make sure to set the movement to walking. Um, you know, this currently should never be, right? There should always be a cued montage every time we transition. But, now I just gave you guys a tool to make transitions to locations. So maybe you use this for other mechanics, right? Like this is kind of a pattern you can keep reusing of just transitioning. And I didn't put anything that specifies that it's a mantle, right? It's just a transition. So you could put any sort of montage. Maybe you want to transition into grabbing a rail and swinging around on it or something. You're going to need transitions if you're going to need the root motion. So this is just kind of a general pattern you can reuse. And then we, of course, set this back to false so that it doesn't keep getting called on the next loop. The last thing we got to handle is the simulated proxy stuff. So come down here and add 2 lines to this. So these are just saying that we want to replicate these variables, the short mantle and the tall mantle booleans, and we're passing the condition skip owner because the owner is the one that generated the mantle. They don't need to know that they mantled. It's only everyone else that needs to know. These are just booleans, and remember we're just toggling these back and forth to call the replicate function. So then the onRep functions, pretty simple. They just play animation montages. Notice they're not playing the traditional montage. They're playing proxy short mantle montage and proxy tall mantle montage. So these are going to be different montages that we create. And you'll see why in the editor. But yeah, that is everything for the code, I believe. Yeah, we'll see what the proxy is doing if that doesn't make complete sense to you. But if you've been following along, hopefully you get what I mean by, proxy, simulated proxies on the clients are handled a little bit differently. Their movement, the actual movement of the capsule is completely handled by the character movement component. You don't need to touch any of that. But you do need to replicate any state that affects stuff like the animation or maybe anything that's driven by particle effects. You need to be replicating that so that the simulated proxies can see it. So let's hop into the editor. All right, so if we go to our third person character and we inspect all of the new parameters we just made, we have this stuff which you can toggle with, you can fiddle with, but importantly we have 6 animation montages that we need to create. Now I already created them and I'm not going to just remake them on camera because I'm not that quick at making animations. It would be boring to just watch me just pose the character, but I will go into them and show you like how I made them and the stuff you need to do, the buttons you need to press. So I do everything in the animations section. So I create my animations through the level sequencer. Just a nice little kind of hidden gem in Unreal Engine. So what does that mean? So if I open up one of these level sequences we'll go to the tall mantle here. So over here's my guy. And to make these animations, I dragged in a block from the level so that I can get a really good reference of how this is going to work. So basically, check out my previous video to find out how exactly I set up this entire level to work like this. But I just can use the IK-rig in the level sequencer to pose the character in this level sequence. This is not an animation, this is a level sequence. And you can see what that looks like. It's just a nice little pop-up here. Nothing... I'm not that good with animations, but yeah, you can see the hands. Yeah, I'm pretty amateur at this, but this is purely a mock-up. I mean, this takes no time, which is so nice. Then you right-click on here and you create a linked, create a linked animation sequence, and you pick where to save it, and then that brings you to this screen. You export it to an animation sequence. So I already did that, obviously. So, like for example, for the tall mantle, my tall mantle is right here. And you can see, you can see it has root motion, but so the important buttons to press here is you need to enable root motion. So without that, it would look like this because this is the root motion, but oddly, enable root motion locks that root motion because now that root motion is being captured by the character movement component. And if this wasn't checked, you obviously want to use normalized and ref pose. I mean, whatever, you should hopefully, if you're doing this, you at least know how to create the animation. So, you can choose what you want your root motion lock to be referenced from. And yeah, that's everything you need to set here. Another important thing, so I make a little bit of space here at the end. So here's the final product. I leave like a good, 0.2 seconds. And that's because we're going to need to also blend out of this. So now let's go to the montage. So then after I make this animation sequence, I right click and I create anim montage from that. And where's mine is right here. And it's just a wrapper for the anim sequence, but you can't play an anim sequence directly. You have to play an anim montage. And the important things here is the blend time in is 0. This is really important. It has to be 0 blend time in, because you want to just be playing the root motion right away. You don't want the blending, gets kind of messy, and it's actually can cause more desyncs. So you blend instantly. The blend out time is like 0.15. That's why I added that little space at the end. So there's just a little bit of time to blend back into the default, standing pose or whatever of the character. Nothing else should really be changed in here, I believe. So, yeah, pretty much other than that, just a standard animation montage with root motion. And then, so I create one of these for the tall montage. So I'll come back to the little Singster shows. One of these for the tall montage. There's one of these for the short montage. Here it is, short mantle. I don't have the right block in place, but you get the idea, same thing. And then I create these transitions. So if I'll go to the transition tall mantle. So basically what I do is I copy the rest pose of the character, which just looks like this. And then I also copy, so you can just go to the tall mantle and Control C copy this pose, this dot on the little Singster, and then I go to the transition tall mantle and I paste that in to right here. So I paste that right there, and then you can see basically it's just a linear blend between these two poses, and that has to be 1 second long. It has to take 1 second for our inverse math to make this be like any time we want. Then I also add a second after this, just of buffer, because if we don't have this second, you can try it without an additional second, but weird stuff happens. And this is my transition animation. So this will be scaled to be fast if we're close, be slower if we're farther away, but this is what's making that transition. So then same exact process, create linked animation sequence, I create that. Then once I have my transition, everything's good. Importantly, no root motion, nothing like that. So then I right click, create anim montage, and here's my transition montage, and it should be the same exact stuff. So blend time in, here you do want blend time in, because here you're transitioning from whatever pose you previously had, like maybe the character was running or falling. They transition into this transition, confusingly enough. But then blend time out is 0, because once they're in this pose, they instantly are going to be in the next pose, which is the root motion animation. If there was any blend time out, the character would start transitioning out of this pose, but they actually want to be directly in this pose so that there's a seamless transition and you can't even tell. Also ignore my horrible animations. I'm by no means an animator. So I follow that same exact process for the short mantle. You can see it's all the same thing. Here's the short mantle montage, and here's the short mantle transition, just going to that pose from like a standing position. Same exact blend stuff. And yeah, that's everything for those. Then the proxies. Okay, so what are we doing with the proxies? So proxy is kind of a full cycle. So the proxy, we're not playing root motion source. transition animations. We're just going to do it all as one animation. And the reason for this is, for one, I'm going to save bandwidth. It would be too much bandwidth to like trigger a transition on a proxy. So we're going to kind of fake it. So how did I do that? I'll just pull this up really quick. The tall mantle. So basically, I allocate like 0.16 seconds to playing that transition in the beginning, and then I just play the regular montage after that, and then I allocate that same time after for the blend out. So there is going to be a blend in this case. So then I create the animation from that. If I go to the proxy, you can see there is a blend in time that's roughly equal to that time I made just to blend from the standing pose to the start of the mantle pose, and there is a blend out time. And this also corresponds with roughly how long it takes to perform the transition in terms of capsule movement. So this just creates a really seamless looking, obviously it's not perfectly realistic, but you cannot tell because you're just spectating like a random simulated proxy, and like movement on a simulated proxy already looks a little bit janky. Anyway, that's Unreal Engine's problem, not mine, but this animation just looks perfectly fine, and we're literally getting away with it with just using 1 bit. So I'm very happy with that. I mean, literally 1 bit to completely replicate the entire mantle is pretty sweet in my opinion, because this scales, remember, right? Like if you have 20 players in a match, you can't be if a mantle took 5 bits, now you're 5 times 20 actor channels or variable channels for that single mantle. Whereas here we're only 1 bit, so 20 people can be mantling all at the same time, and that's only 20 bits of bandwidth being used for the mantle. So I thought that was a pretty clever solution to this. And as you can see, when you plug it all in, yeah, we did plug it in. I already plugged it in, so you need to go plug it in. So let's check this out finally. So here we are hopping into multiplayer. Oops. So first we'll just show the whole thing. So come to this wall, press space, boom, popped up over the wall. Awesome. So also, if you watch on the client screen, here I'll make this a little bit bigger. If you watch on the client screen, I can walk up to the surface and I can mantle it, and you can see those animations playing on the client. Serviceable, not perfect, but it definitely gets the point across, and I would say it looks like it's quality. It looks like something you would find in a game, and it's good enough. The proxy animations are good enough. Like if I come over to this wall, on the owning client, like if you look at the server screen, the animations look great. Like everything, obviously the hand IK stuff, the hand can clip through the wall. That doesn't look great, but like the feel of the animations looks pretty darn good. But what I was saying is the proxy feel. So like if I come to this wall and you look on the client screen, you can see that it looks like it's transitioning a little fast. That hand kind of clips the wall early. That's because if you look, this is kind of the largest transition distance we can possibly do. The red capsule's got to go all the way to the yellow capsule. So this is the worst case. And that could be because, I probably shouldn't have made the short mantle height be this large. I maybe should have made a medium mantle height. I would get higher fidelity in general. But, we could also maybe send a float to proxy clients indicating transition length, but then you're wasting a float that's multiplied by every proxy in the game. Sometimes you gotta just say good enough, and especially when if you look at the client screen and you look at the movement of the character on the server anyway, it's not like super high quality. Like it's pretty choppy, and that's not something we can fix. That's Unreal Engine's. That's like as good as Unreal Engine can make it. So if the movement itself isn't buttery smooth like it is on the owning client screen anyway, are they really going to notice when this animation is just like a tad off? Like probably not, but of course it's completely up to you, and you can make it higher quality if you want to. And then obviously another big test is go on the client and do all this, and as you can see, everything is working and we are not hitting any network problems, so pretty sweet. Yeah, really, I think mantling is such a good mechanic because it ties in like map interaction so well. Like, a cool thing I realized to demonstrate like all the stuff we've been doing is, you could slide down here, and then I missed it. That's awkward. You could basically slide down here and then catch this really far away surface. I can't get the jump right. So yeah, another thing I found this. So I'm going to quickly turn off the debug so that we can see everything a little easier and go back in the editor. So I just put that as 0. Alright, so now we can see everything a lot more clearly. My graphics card is still dying, but at least you can see how clean everything looks. And I also found a cool little thing that ties kind of all the mechanics we've been doing, or not all of them, but a couple of them together. So if you slide down this and jump off, you can grab this really far away ledge, which, if you look, let me frame this from the client, because it's pretty cool, like showing, that's going to be an issue, showing all the stuff we learned. So come up here and show you guys that. Whoops. You guys have no idea how tough my computer is, how hard my computer is struggling right now. So we slide down here, jump, catch on that. It's pretty cool. So it's combining our slide, our mantle, the other stuff we made, like the crouching, and yeah, it's just bringing it all in one. And that's what makes, that's what's key to making just a cohesive movement game, is just having all these mechanics that the player can utilize to express themselves and how they can move around the map. So it's really fun, and especially mantling just provides so much complexity and interconnection, because every surface becomes a potential spot that you can move to, just given your creativity and your platforming skills, right? So we'll do a couple quick tests to prove everything's good for networking. So we'll show net corrections. So on the client, you can see when we get a correction, so obviously there's none, you can't tell that, so let me try to make one. Usually collisions will cause them. Just does not, it wants to be too good, I guess. Well, when you get there we go. So these are net corrections, so it's showing the green is showing where the capsule was supposed to be, and the red is showing where it was. You get that very easily by colliding into non-replicated physics objects. But as you can see, when I do the mantle, nothing. It's spotless because everything is perfectly in sync. You get one. Okay, actually, that's also something I want to talk about. I've been noticing recently, I've been getting net corrections when I was doing the dash we implemented a while ago. And this is so frustrating. I also spent so much time looking at this. I still can't exactly figure out why. There's just a slight hiccup. It luckily doesn't affect the dash that much, because it's like not that big of a difference, and the rest of the dash works perfectly. It doesn't really provide a noticeable difference, but it can be compounding. So I'm probably gonna make a video doing a dash 3.0 where I not only fix that, but I do even more stuff, because I don't know, to be honest, the dash 2.0 was just to show how you make root motion, but the dash itself kind of sucks. I'm thinking I like the idea of how I made the grab mechanic, the mantle mechanic. I liked how I made it very polished. I think it gave people more of a feel of a real mechanic, and so I might do that for the dash 3.0. I might make like a really good dash, that something I would even put in like my game, and then you can really see polish, and I can fix that annoying problem. So sorry, I didn't realize that when I made the last video. So sorry for people that implemented that, and now they technically do have a movement unsafe problem in their code, but it's not super big. But then another thing I want to show you. So I'll go emulate packet loss. Sorry, not packet loss, packet lag. We'll put a ping of, say, 200. That's a pretty bad ping. So you can see if I run in front of the server here, you can see when I move, I'm 200 milliseconds in the past. And, you know, I can mantle to stuff, and everything seems to work just fine. So, you know, until you start to see those red dots, then, you know, everything is completely in sync. And, yeah, and we're getting no net corrections, so everything's working just as intended, which is pretty sweet. Whoops. The last thing I want to show before I end this video, because this is probably going to be an insanely long video, is packet loss. So I think I might have showed this before, but packet loss is basically when you drop packets. So this is going to force net errors. Like, you're going to have net errors. Like, you see them right there. That's because you're just not getting all the packets sent. There's no way to avoid this. But one thing I just read, I don't know how true this is, so it takes it with a grain of salt, but I read this and it seems reliable, which is that UDP packets, a good, like, worst test case kind of, is a 1% loss. So if you have 1% loss on all UDP packets, that's apparently like, you know, maybe not the worst possible case. You know, it could maybe get up to 5% loss, which is just brutal. But that's a good, like, worst possible situation of UDP packet loss that you could test in. So now, from now on, I test most of my movement logic. At least when I'm done with it, I test all of my movement logic at 1%, which is doing this command, the net emulate packet loss 1. That is simulating 1% of all packets just being dropped. And, you know, as you can see, it's holding up pretty well. Like, most of the time, you probably wouldn't notice. And if I turned off the airlines, you probably wouldn't even be able to tell that this was erroring out. But that was something I just did that I want to show you, is if you look at the dash, you can see I get multiple corrections with the dash. And that's why I'm want to fix this, especially, is because you get, whenever you have a single error in a whenever you're playing with lag and you have a packet drop, then yeah, just like that, you get compounding errors. So that's not like that example wasn't a problem with the mantle. That's a problem because we dropped a packet somewhere in this process. And whenever you're out of sync, especially when you're playing at a high lag, you get that compounding desync. And that is, you know, that's really bad, especially if it's something that's a program bug, like the dashes, then, you know, that's going to happen every time. Whereas if it's just a packet drop, like sometimes when I mantle, you might see the error. That's not going to happen every time. But when it does, obviously, if you're at a high enough ping, the compound will be even greater. So basically, all I'm saying is, like, when you're playing at a high ping and a high packet loss, which unfortunately usually those two go together, like if you just have a really bad Wi-Fi, then you're going to start seeing this worse performance. But like right now, we're simulating 200 ping and we're simulating 1% packet loss, which is a pretty bad case. Like, normally packet loss is around like maybe 0.5%, maybe 0.2%, and your packet lag, your average lag, I think, is around 40 milliseconds globally. That's like something like Amazon's like global latency average, and this will play fine. Like, this is, you know, you probably would barely even tell that you're actually playing a multiplayer game. So yeah, like, you test for the worst case scenario, but obviously at the end of the day, just check on how it looks at the average case, just that you just have that peace of mind. Like, you know, the game still runs like a AAA game, which I would say the movement right now runs like that. Like, everything just is clean. There's no lag. I mean, this is completely multiplayer, and we're experiencing really no hiccups at your average user's conditions. So yeah, pretty sweet. Obviously, besides the dash is all fixed, but yeah, that was definitely a long video, but I hope you guys got a lot out of it. I hope you guys learned a lot, and yeah, if you have any problems, go to the Discord, I guess. I'll be there. I'll help you guys out. So, and also go to the Discord if you want to give me any more ideas of topics you want me to cover on the character movement component. So yeah, thanks for watching. If you made it this far, the brave, the few that made it all the way to the end. See you guys in the next video.